In this video, we're going to talk about 6.3 matrices for linear transformations. Let's start with problem number 1, and it asks us to find the standard matrix for the linear transformation T, where T of x, y is given as x plus 2y, comma, x minus 2y. So that turns into the standard matrix of 1x and 2y and 1x and negative 2y. Just that easy. Number 3 says T of x, y, z is equal to x plus y, x minus y, z minus x. Be careful with this one. We still need to keep our columns in order, or our variables in order here. So I have 1x, 1y, and 0 z's. I have 1x, negative 1y, and 0 z's. And I have a negative 1x, 0y, and 1z. Don't get confused by the way that they wrote these. X's before y's before z's. Keep all of your x's in one column, all of your y's in another column, all of your z's in another column. Okay. Let's look now at number 7. Number 7 tells us to find the image of a vector. So use the standard matrix for the linear transformation T to find the image of the vector V that's given. So 7 says transformation is given T, x, y, z is equal to 2x plus y, 3y minus z. So it takes a 3-dimensional vector and turns it into a 2-dimensional vector with vector v. V, my input here, is 0, 1, negative 1. So I want to find T of 0, 1, negative 1 is 2 times 0 plus 1, 3 times 1 minus a negative 1. So that is going to be, oh, I want to do this with matrices. We've already done it that way before. So this is T of x, y, z is equal to matrix A times V is, so we're going to make the matrix here 2, 1, 0, 0, 3, negative 1 for my transformation matrix. And we have vector V here is 0, 1, negative 1. And that gives me 0, 1, that's 1, 0, 3 plus 1, that's 4. So T of 0, 1, negative 1 equals the matrix 1, equals the vector 1, 4. Let's go ahead and look at number 11. T of x, y is equal to negative x, negative y. V is equal to 3, 4. So again, we want to find that transformation matrix, which is going to be negative 1, 0, 0, negative 1. And then we want to use that transformation matrix to evaluate the transformation of vector V. Like so, which makes sense. Opposite of x, opposite of y. For the transformation, we get opposite of x, opposite of y. Transformation 3, 4, negative 3, negative 4. All right. 15 says that T is the counterclockwise which you might want to just abbreviate CCW, rotation of 45 degrees in R2 with V equals 2, 2. So when we want to add angles here, this is going to be T, and this is given in the book. So you can go back and look at your example problems to see where this came from. But if you rotate theta here, this is going to be cosine of theta x minus sine of theta y, comma, sine of theta x plus cosine of theta y. So that's my transformation. So I'm going to stick in here to evaluate cosine of 45 degrees, root 2 over 2 x minus root 2 over 2y, root 2 over 2x plus root 2 over 2y is my transformation here. xy, not doing anything with v yet, but I just want to turn that into a t of xy is equal to a x, like that, which in this case is going to be vector v, but I'm going to have root 2 over 2, negative root 2 over 2, root 2 over 2, root 2 over 2, multiply that by vector v, which is 2, 2, and I get root 2 minus root 2 and root 2 plus root 2. So that's going to be 0 to root 2. So t of 2, 2 is equal to 0 to root 2. Look now at number 21. T is the projection of the vector W equals 3, 1 in R2, which using formula here, TV is equal to projection V with V equal to 1, 4. So from calculus 3, we have the formula projection A onto B. I think is the way to read that is dot product of A and B divided by magnitude of B squared. Let me write this over here. Projection B to A dot B magnitude of B squared times vector B. I used that in the last video and I didn't write the formula for it. So I'm sorry, but that's the formula that I'm using there. So the projection of the vector W in R2 here is going to be, and we have W is 3, 1 dot, and we're just going to use, this is just to get my transformation of xy here. So I'm going to use a generic xy over the magnitudes of 3 squared plus 1 squared is 10. That's just the Pythagorean theorem, not putting it under a square root sign, times 3, 1. So this is going to be 3x plus y over 10 times 3, 1 is 3/10 times 3x plus y, comma 1/10 times 3x plus y is 9/10 x plus 3/10 y, comma 3/10 x plus 1/10 y. So that makes my transformation matrix here. Capital A is equal to 9/10, 3/10, 3/10, 1/10, and I guess that's A. That's my transformation matrix. So B asks me to take T of V, which is AV, which is 9/10, 3/10, 3/10, 1/10, times V is 1/4. So that's going to be 9 and 12 is 21/10, and 3 and 4 is 7/10. So that makes T of 1/4 equal to 21/10, 7/10. Number 25. T of x1, x2, x3, x4 is equal to x1 minus x2, x3, x1 plus 2x2 minus x4, x4. Write all that down right. X1 minus x2, comma x3, comma x1 plus 2x2 minus x4, comma x4, and V is equal to 1, 0, 1, negative 1. So transformation matrix A, for part A here, is 1, negative 1, 0, 0, 0, 0, 1, 0, 1, 2, 0, -1, and 0, 0, 0, 1. So that's matrix A. My T of X, which is all this stuff is X, is equal to 1, -1, 0, 0, 0, 0, 1, 0, 1, 2, 0, -1, 0, 0, 0, 1 times x1, x2, x3, x4. So T of V is equal to 1, -1, 0, 0, 0, 0, 1, 0, 1, 2, 0, -1, 0, 0, 0, 1 times V was 1, 0, 1, -1. So that makes this 1, and 0 is 1, 0, so that's 1, 0, 0, that's 1, 1, 0, 0, so we're at 1, plus 1, that's 2, and this is -1, 1, 1, 2, -1, so my T of V, which equals my T of 1, 0, 1, -1, is 1, 1, 2, -1. Let's move on now to number 35. And 35 asks us to find the inverse of the linear transformation. So we're going to use that by finding the inverse of the matrix. So x1, x1 plus x2, x1 plus x2 plus x3. Okay, so that gives me a matrix A for my transformation, 1, 0, 0. And then I have 1, 1, 0, and then I have 1, 1, 1. And all I need to do first to determine if this has an inverse, or if we can find an inverse, say, is to take the determinant of this matrix. So because this is a triangular matrix, I can just multiply across the diagonals here to find the determinant. And I'll find that the determinant there is 1 times 1 times 1, which is 1. So determinant of matrix A is 1 times 1 times 1 is 1, which is not 0, so it has an inverse, it's not singular. So then we can go ahead to try to find A inverse by doing A augment I and use elementary row operations to get this to turn into I augment A inverse. I'm just going to use some technology to do that. So set this up as 1, 0, 0, 1, 1, 0, 1, 1, 1, 1, 0, 0, 0, 1, 0, 0, 0, 1. And I want to RREF that. I'm going to get 1, 0, 0, 0, 1, 0, 0, 0, 1 on this side. And on this side, I'm going to get 1, 0, 0, negative 1, 1, 0, and 0, negative 1, 1, like that. So that tells me that my inverse of my transformation here is x1, comma, negative x1 plus x2, comma, negative x2 plus x3. Let's look at number 37 now. 37 asks me to find the image of the transformation two ways. First using the standard matrix, and then using the matrix relative to B and B prime. We did that in an earlier video. So T is given as R2 to R3. And then we're told T of XY is equal to X plus Y, X, Y, like that. V is given as 5, 4. B is given as 1, negative 1, 0, 1, and B prime is given as 1, 1, 0, 0, 1, 1, 1, 0, 1. So first thing, let's find the standard matrix. A, they're going to call it A prime, is equal to, and we have 1, 1, and then we have 1, 0, and then we have 0, 1. So that means that T of V is A prime times V is 1, 1, 1, 0, 0, 1 times 5, 4, which is going to be 5 plus 4, 5, and 4 is 9, 5, 4. So T of V is equal to 9, 5, 4. That's the first way. That's kind of the easy way. Now I need to actually transform all of these vectors that are in B. So T of 1, negative 1, and I need to, however I do that, I'm just going to use the transformation definition. There's no reason to actually use the matrix here, but 1 plus negative 1 is 0, and then we have 1, and then we have negative 1. And then I need T of 0, 1, which is going to be 0 plus 1 is 1, and then 0, and then 1. So now how do I write these in terms of these vectors that are in B prime. Again, we have a whole video on that. I'm not going to go through the whole process of doing that. But you can find the linear combination of these for this to be one of the 1, 1 zeros plus 0 of the 0, 1 ones minus 1 of the 1, 0 ones. Zoom out just a little bit so I can write that all on one line. Okay, and this one you can find as 0 of the 1, 1 zeros plus 0 of the 0, 1 ones plus 1 of the 1, 0 ones, since it is 1, 0, 1. So that means t of 1, negative 1 the b prime down here is equal to, and we're going to read these coefficients here, 1, 0, negative 1, and t of 0, 1 b prime equals, and read these coefficients here, 0, 0, 1. So that gives me a not a prime up here, but a of 1, 0, negative 1. I'm just writing these down here as column vectors, like that. Then because v respect to b is equal to 5, 9. If you want to go back and see that, then b with respect to b, you can go ahead and take 5 of these and 9 of these to get the 5, 4, 5, negative 5 plus 0, 9. 5 plus 0 is 5. Negative 5 plus 9 is 4. And that's v. That's what they're saying by that, is that this is 5 times 1, negative 1 plus 9 times 0, 1. That's where they're getting the 5 and the 9 for down here. We have t of v b prime is equal to a times v b, which is equal to 0, 0, 0, negative 1, 1 times 5, 9, which is equal to 5, 0, negative 5 plus 9 is 4, meaning that t of v equal to 5 times 1, 1, 0 plus 0, times 0, 1, 1 plus 4 times 1, 0, 1, which is 5, 5, 0 plus 4, 0, 4, which is 9, 5, 4, which is exactly my same answer that I got up here. Those are the same. We found the answer two different ways. Let's look now at number 45. And this is using the differential operator from calculus. Actually, you'll see this differential operator in differential equations. We have let B equal the set of 1, x, e to the x, and x, e to the x. These are all functions that are linearly independent, so they form a basis, and that's what B is. So is a basis for a subspace W of the space of continuous functions and let d sub x like that be the differential operator. On W. 45. Find the matrix for the transformation of the operator d of x relative to the basis B. So what I need to do is find the derivative of 1, 0. The derivative of x is 1. The derivative of e to the x is e to the x. And the derivative of x, e to the x, I'm going to have to use the product rule, is going to be e to the x plus x e to the x. So this is 0 times 1 plus 0 times x plus 0 times e to the x plus 0 times x e to the x. This is equal to 1 times 1 plus 0 times x plus 0 times e to the x plus 0 times x e to the x. This is 0 times 1 plus 0 times x plus 1 times e to the x plus 0 times x e to the x. And this is 0 times 1 plus 0 times x plus e to the x, so 1 e to the x plus 1 x e to the x. So my matrix here, A, is going to look like this. 0, 0, 0. Sorry, writing these down. 0, 0, 0, 0. 1, 0, 0, 0. 0, 0, 1, 0. and 0, 0, 1, 1. So, and that keeps my all of my constants are in a row here. All of my x's are in a row. All of my e to the x's are in a row, and all of my x e to the x's are in a row here. Now let's use what we just found there as our transition matrix on number 47 to find the derivative of 4x minus 3x e to the x. And so that's going to be, I'm going to write 0, 1, 0, 0, 0, 0, 0, 0, 0, 0, 1, 1, and 0, 0, 0, 1. And down here, this is going to be 0 for the constant, 4 for the coefficient on x, 0 for the coefficient in front of e to the x, and -3 for the coefficient in front of x e to the x. So let's slide this down. And that derivative should be 4, and then 0, and then -3, and then -3, which means that this should be 4 plus 0x minus 3 e to the x minus 3x e to the x. Now, if you actually differentiated this using the different pieces, the different rules here, derivative of 4x is 4, the derivative of -3x e to the x is -3 e to the x minus 3x e to the x, and you would get that as the total derivative, but this is how it was done with matrices, and this is most likely the way that your computer algebra system in a calculator that can compute derivatives, so on, would be able to do this. It would probably use matrices to figure out the coefficients like that. So that's it for this video, and that's it for chapter 6. So we'll come back next time and talk about 7.1, which will be our last topic that we will cover in this set of linear algebra videos. So have a good day and see you for the next video.